Let's rewrite our energy conservation equations using the derived heat flux term from Fourier law of heat conduction. Okay, so we have d over dt, rho x, cp x, T, which is uxt. So this is the temperature, is equals to minus d over dx, k x d over du over dx. This u is as function of x and t, plus some heat source. So okay, there is a negative sign here. So the negative sign will cancel out. Will be d over dx, kx du over dx plus q. Okay, so this is the change of the rate of change of the heat energy will be equals to the heat flux, which is the heat flux is represented by the temperature and the heat source. And let's assume where we usually do these assumptions in the engineering perspective, but sometimes you have to think about whether this assumption is validated or not. But for simplification, let's assume here, assume my rho, this density of the material, the Cp, the heat capacity of the material, as well as my heat conductivity of the material is constant. That means it's not as function of x here, so they are all constant. Then if they are all constant, what we can have is rho Cp d over dt u xt is equals to k d squared u, the second derivative of space. Let's also assume that the Q is 0, so there is no heat source, there is no chemical reactions, there is no magnetic heating or something else. There is no heat source, so the Q is equals to 0. And since they are constant, we can also rewrite as ut. So this is the first derivative as function of the time is equals to k over rho Cp. Uxx, which is the second derivative of space, which is the 1D space, so it's only at dimension of x. After we assume rho Cpk is constant and q equals to 0, we derive that ut equals to k over rho Cp uxx. And this is my effective thermal conductivity. And it's positive number, then think about our original form of the heat equation is ut equals alpha squared uxx. So this is a positive number, and that can be represented by alpha squared. And that is exactly the same format ut equals to some positive number times uxx. So this is the 1D heat equations. And that's how we derive from physical phenomena, from energy conservation law, from Fourier observations to our PDEs, which is the simple 1D heat equation PDEs. Okay, then the next part is basically how we can solve this PDE. What kind of conditions we need to have in order to solve such PDE. Okay, so the equation describes the physics, which is 1D metal rod heat transfer, but we need more information to solve the problem. Okay, we need more information to solve the problem, to solve this PDE. What kind of information we may need? So it can be some initial conditions. What kind of initial conditions usually given for this kind of heat transfer Bundy problem? It's usually uxt, which is temperature as function of x at time equals to 0. So at initial time equals to 0, the initial temperature distribution along this whole route is some function fx. This function can be constant temperature, it can be some Gaussian distribution, it can be any function as function of x. Then it's not enough. You also need to combine with some boundary conditions usually. Conditions. Well, the general type of the boundary conditions for this heat equations is usually like what kind of temperature for the initial, basically the tip of the initial x equals to 0, that temperature, and when the boundary at x equals to L, the temperature distribution. So the general type is what happened at x equals to 0 and x equals to f, okay? So some common boundary conditions, okay, some boundary conditions. For example, some common boundary conditions look like the first periodic. So we have U0 T, so temperature at the initial tip at all time equals to UL T at all time. Then it can also be a fixed temperature. So what is fixed temperature look like? Means U0 T at all time at the initial tip of the rod is equals to UL, which is the left side of the rod is one temperature constant. And at x equals to L at all time equals to U right side of the rod, okay? So the UL and the UR are some constant number represent the temperature of the rod at two different ends. Then it can be isolating. So isolating means there is no temperature gradient of the end of the rod. So it's Ux, the first derivative of x as the temperature first derivative as function of x, 0T equals to Ux LT. So two ends of the rod for the temperature gradient will be equals to 0 to represent isolating. Then the next part is based on those boundary conditions, can we solve our temperature distribution of the rod? And how we can use our own words to describe the physical observations from our solved PDE. Okay.